let's take a look at some predictions from kinetic theory for expected molar specific heats for various gases and what observations around room temperature tell us about the theory. So the simplest case we could think of would be a monatomic ideal gas. There's one atom. It should be like a little tiny sphere, so classically we wouldn't expect any rotational inertia, so there are only 3 degrees of freedom. Motion in the x, y, and z axis. So with 3 degrees of freedom, our energy per mole should be 3/2 times the gas constant R times our thermodynamic temperature. So that would mean C sub V should be 3/2 R. So 3/2 times 8.31 joules per mole Kelvin is 12.5 joules per mole Kelvin. Our constant pressure heat capacity should be R more than that, so 3/2 R plus R is 5/2 R. 5/2 times 8.31 joules per mole Kelvin is 20.8 joules per mole Kelvin, and we'd expect our ratio of specific heats, C sub P over C sub V, 5/2 R over 3/2 R, R over 2 cancels, we'd get a ratio of 5/3 or 1.67. So if we take a look at gases like helium and argon. Helium and argon around room temperature have constant volume heat capacities of about 12.5 joules per mole Kelvin, constant pressure heat capacities of about 20.8 joules per mole Kelvin, and gammas of 1.67. That exactly checks out with an idea that came about from just thinking statistically and doing Newton's second law again and again and again and again and again. So all of those material properties that we talk about in a physics book, all of them should have some underlying physical theory that we can predict what a value should be, test it, and if our theory is correct, expect to observe no difference. Now, ideal gases and noble gases are almost thought of interchangeably because the lighter noble gases, helium, neon, argon, to a lesser extent, krypton and xenon, they tend to behave following the predictions of kinetic theory very, very, very well as long as we're dealing with dilute gases. We don't have super, super high quantities of molecules per volume. Now, the next most complicated thing we could do is make a diatomic molecule. And a lot of atmospheric gases are at least diatomic molecules. So an example could be hydrogen gas. Hydrogen gas is 2 hydrogen atoms connected together. Oxygen gas, nitrogen gas, 2 hydrogen atoms, not 2 hydrogen, 2 nitrogen or 2 oxygen atoms connected together. And the molecules would look kind of like little barbells. So in addition to moving in the XYZ direction, they have 2 unique rotational directions. One would be if we draw the line of the bond between the 2 and imagine rolling around the line of that bond, that's 1 rotational degree of freedom. The other would be if the barbell was spinning around its center of mass. And even though there are 2 axes we could use for that dimension, we could use the z-axis, we could use the y-axis, those aren't unique. They have the exact same moment of inertia, so we have 5 unique degrees of freedom. So we'd expect to have 5/2 times R times the thermodynamic temperature for our energy per mole, so C sub V should be 5/2 R, and C sub P should be 7/2 R. Which would be 29.1 joules per mole Kelvin, and gamma would be 7/2 R over 5/2 R, or 7/5. So if I take a look at hydrogen gas around room temperature, we get a value that's a little bit low for C sub P, and I kind of flipped how I wrote things here for this middle bit. My C sub P value for hydrogen is 28.8 joules per mole Kelvin. My C sub V value is 20.4 joules per mole Kelvin. So it's a little bit under the 5 degree of freedom prediction, and I get a gamma of slightly more than 1.40. I get 1.41. For oxygen, I get 29.4 joules per mole Kelvin instead of 29.1 joules per mole Kelvin. for C sub P. For C sub V, I get 20.1 joules per mole Kelvin instead of 20.8, but I do get a ratio of 1.40, so oxygen's a little high, hydrogen's a little low from the prediction, but they're still pretty close. If I want to make things more complicated, I could go to an atom made of many molecules, like methane or water vapor, and those molecules would have at least 6 degrees of freedom. So the 3 different axes of linear motion plus 3 unique rotational axes. So we would get different moments of inertia around any axis of rotation that we could choose for those molecules. So that means then that with 6 degrees of freedom, we would have 3R for our constant volume specific heat, in theory, about 24.9 joules per mole Kelvin. We would have 4R for our constant pressure specific heat, 33.2 joules per mole Kelvin. So here I went back to the ordering up here. My constant volume heat capacity for water vapor is 27. For methane, it's 27.1 joules per mole Kelvin, which is significantly larger than the kinetic theory prediction. With constant pressure heat capacity, it's a little bit more than R larger. 35.4 joules per mole Kelvin for water, 35.5 joules per mole Kelvin for methane. It's a change of 8.4 instead of the 8.3 we'd be expecting from the universal gas constant, and our gamma values are a little bit smaller. They're 1.30 and 1.31 for those gases. So they're close, but clearly these errors show there has to be more than just this simple ideal gas law theory going on, and that more involves diving into quantum mechanics, which is a topic for a later course. Thanks for watching.